This will be very high level, and this series of webinars I'm offering over the next couple of months will lead up to a one-day course I'm offering in July, and I'll talk about that more later. So I would like this to be kind of an informal situation. So if anyone has a question, just put it in the chat and I'll try to keep an eye on that as we go along. So just a little bit about me before we get into the meat of the presentation. My name is Paige, and I've been an engineering consultant for a little over 10 years now. I first became interested in this work when my hometown flooded when I was a senior in high school back in 2008. And that experience of seeing a community so devastated by a large flood event got me interested in more resilient infrastructure, better planning, and just the power of water in general. I'm sure many of you in the civil field can relate to wanting to help people like that. But I've been using HEC-RAS my entire career for a variety of applications. Of course, floodplain mapping for FEMA, LOMERS, CLOMERS, that kind of thing. Stream bank stabilization, a little sediment transport, dam break analysis, and a lot of cool projects I've been fortunate to be involved in. In November of 2023, I took the leap and I started my own company called Surf City Hydraulic Engineering. I live in Huntington Beach. That's why I named it Surf City. And in my free time, I like to run, hike, and enjoy Southern California in general. So this slide's just a little overview of what we're going to be covering in the next hour. I'll go over and whoever that is, can you mute? Because, yeah. Whoever that is, could you please mute? I cannot figure out who that is. Okay. Let's see. I think I got it to work. Thank you, Eric. Yeah. Thank you very much. So anyways, this presentation will cover briefly the history of HEC-RAS because it has changed since the program came out in 1995 drastically. Then I'll go over a little bit of 2D theory, as in what's behind the black box of the program, some differences between 1D and 2D hydraulic modeling, applications that are appropriate for 2D modeling, the data requirements for building a 2D model, and then I'll quickly go over a typical workflow, and then hopefully we can get into the software a little bit and answer some questions at the end. So here's just a breakdown briefly of the history of HEC-RAS. Like I said, it's changed a lot, even since I started working in the industry back in 2013. It has changed drastically. And the 2D capabilities have gotten so much better than when it first came out. So it's really a cool time to be a HEC-RAS user. The software first came out in 1995 after the Fortran type predecessor called HEC-2. And then a couple years later, unsteady flow modeling was introduced. And then eventually there was a geospatial capability, but you had to use an outside program that would make GIS and HEC-RAS compatible, and it was called HEC-RAS. I don't know what's... Don't really know what happened there. Well, anyways, 2D modeling came out in 2016, and at that time, they also included HEC-RAS mapper. And HEC-RAS mapper allowed you to do pretty much everything within HEC-RAS. And HEC-RAS mapper has gotten better and better over time to the point you don't even need a GIS license for the most part to do what you need to do in the program. Everything's very seamless. You can import geospatial data and export very easily, which was not always the case. And then in 2024, they came out with the capability for stormwater pipe networks. That was something that people were asking for a long time. That was funded by the city of Chicago, but because the Army Corps is a federal agency, anyone can use that. And something of note is HEC-RAS 2025 is being worked on right now. This will be basically another overhaul of the program. The graphical user interface will be updated significantly from this kind of current 90s vibes graphical user interface to something that's a lot more modern. They're improving the meshing capabilities significantly, and you can download that now in the alpha version. The Army Corps has been very clear that it's not ready for project use, but it's kind of cool to play around with if you're interested. Sorry, guys, I don't know how to get rid of this line. Does anybody know? Let's see, maybe I can try unsharing and then.
If you go to the control panel where it says annotate, there should be a control that says erase my drawing.
Oh, I'm sorry, annotate. Oh, I think it's gone. Thank you so much, Jackie. Let's see, Okay, so there are a number of 2D modeling software programs out there, so why would one use HEC-RAS? Well, the obvious reason is because it is free of charge. Other programs like Flow2D, 2Flow, Mike, they cost money. And the licenses are actually fairly expensive. That can make it difficult for other people to look at your model if they don't have that license, and not every reviewing agency has those licenses. But anyone can download HEC-RAS from around the world. In fact, it's widely accepted around the world. People in Australia use HEC-RAS, and of course, I think Canada and other places in the world. The slides are no longer visible. Thank you. Okay. Can you see it now? And there's no line. Great. Okay. Thank you so much, guys, for your patience. Where was I? Yes. Okay. And then I will say the Federal Highway Administration does have a 2D program as well. It's called SRH2D. And if you're focused on a bridge and you're doing more near field hydraulics, that is probably the way to go, even over HEC-RAS. But if you're looking into more of a floodplain modeling, more of a riverine tip situation, then HEC-RAS is a good way to go. And then another reason HEC-RAS is special is the subgrid approach, which we'll talk about in another slide. So now let's talk about what is 2D. I'm sure if you signed up for this webinar, you probably have some hydraulic modeling experience, and you're probably used to 1D modeling, which is unidirectional. The flow direction is prescribed by the user using a river center line and then a series of cross sections. It's depth average, and then there's the steady state and unsteady state capability. 2D modeling has a lateral flow component. So instead of just looking at one direction of flow, you can see how things move in two directions. It's also depth averaged, and you can only do unsteady flow with 2D, no more steady flow. However, you can do what's known as a quasi-steady type model, where you put in the same flow rate for every time step. And in that way, you kind of simulate that steady flow situation that is common in 1D modeling. And then this is way beyond the scope of this presentation, and I don't have any experience with 3D modeling, but it is becoming more common. It is very expensive, but you get that vertical distribution through the water column. So if that's something you need to understand, you need a 3D model, or they call it CFD, computational fluid dynamics. The software programs are very expensive. It's very time intensive, but it will give you that vertical flow information if that's what you're looking for. So this table is kind of a summary of what I was just talking about with 1D versus 2D, where we're seeing that 2D modeling, everything's mesh related, but you get that lateral flow information. Transverse velocity and momentum is computed. Your velocity is averaged over cross-sectional area or depth that you're at a point in a mesh. And then another thing to point out that's different on this slide is the eddy viscosity. This, in 1D modeling, that's accounted for in the like catch-all meanings in. And then in 2D modeling, you can have this information, but you have to use the full momentum equations. And I'll talk about the full momentum versus diffusion wave in a future slide, but this is the default in HEC-RAS, and you don't get eddy information. And then as far as information you need to build a 2D model versus 1D, of course, for both, you need elevation or terrain information. It's just the format in which that terrain data is presented that's different. For 1D modeling, it's going to be surveyed or cut station elevation cross sections. And I will say, if that's all you have, you can turn that into a format that's suitable for 2D. And that's common for a situation where you don't have bathymetric data. You just have LiDAR that gets the water surface, but you need the information underneath, so you can burn that in to a raster. And then both 1D and 2D has the capability to include bridges and culverts. That was not always the case. 2D modeling took a couple of years to add that, or the Army Corps took a couple of years to put this into 2D, but it's in there now and it works really pretty well now. When they first released it, it was a little buggy and the models were pretty unstable, I feel like, but it's gotten a lot better. So I guess if you're deciding whether to do a 1D or 2D model, here are some questions asked. From a more technical standpoint, the two major questions are, is the primary direction of flow clearly defined? For example, do you have just a straight concrete channel? I mean, for something like that, you really don't need a 2D model. 1D is very appropriate for that. Same if you just have a stream or riverine situation that's pretty clear cut. Where 2D comes in is if the main flow path isn't very clear. Is there a lot of split flow? Is there a lot of braiding in the stream? These are all good situations for 2D modeling from a technical standpoint and even from a standpoint of presenting the results. And that's just the technical side. There are, of course, other more project-related considerations. I would say the biggest one being, will the regulatory agency you're working with accept this modeling program? Because a lot of times the regulations are written for the more common 1D modeling that we've been using for the past couple of decades. And now places are starting to catch up and 2D's becoming more common, but not everywhere. You also have to consider what data do you have available. And if you need to compare your results to an existing model. If you have a HEC-RAS model and you're just building in a small area and it's going to affect one cross-section, is it really worth building a 2D model and then messing with those differences between 1D and 2D? I don't know, probably not. Clients probably aren't going to pay for something like that, so those are things to consider before you dive into a 2D model. And here are some very common situations that where 2D modeling is appropriate. Of course, floodplain modeling for complex floodplains. FEMA has come out with even encroachment guidelines for 2D modeling. So you can model encroachments now in HEC-RAS 2D. Alluvial fans, that's another good application for HEC-RAS 2D. Dam break analysis, and now you can also do sediment transport with 2D. And the Army Corps has been putting out a lot of great information for that and a lot of good YouTube videos if that's something you're interested in. I don't have any experience with that, but it's there. You can also do urban and fluvial flooding now. They just recently put that out last year with the stormwater pipe networks, but everyone was really excited about it. River restoration, you can use terrain modifications to simulate log jams or things you would put in a river restoration project. Fish passage, channel stabilization. There's also ways to do modeling for non-Newtonian fluids if you're interested in mud or debris flow. And like I said before, these complex junctions and split flow, it's great for 2D. And instead of sitting there trying to, finagle your cross sections and then model the junctions just right and figure all of that out, sometimes it's easier to just draw a mesh and knock it out with a 2D model. Let's see, it looks like we have a question. I have a question. We usually. Thank you. Yeah, this question is about rain on grid modeling. Yes, that's another good application for HEC-RAS. There is a debate on the, I guess, accuracy of those results. I like to use HEC-HMS more often. And the reason is because rain on grid models, you have to have the entire catchment in HEC-RAS for it to work. So you have to have a DEM in there that covers your large catchment area, which you said could be more than 100 hectares. That creates some pretty large file sizes, and it can be difficult to share that information. And then you can't realistically get a very fine spatial resolution on that. So your results are kind of questionable in that way. A good workflow for that would be to put your rain on grid model in HEC-RAS, maybe use a more coarse DEM, and then get your hydrograph for the area of interest, create another model with a better, more fine spatial resolution for your area of interest, and create that as an upstream hydrograph using your rain on grid model. But I would not use rain on grid alone for, I guess, detailed hydraulics, if that makes sense. Does that answer your question?
Yes, thank you, that you answered correctly. Yeah, because we just working on a big catchment project that can be more than 1,000 of kilometers square. So usually they are using this training grid model as they are taking it very easy, just apply curve number and Manning coefficient, roughness, and the value of the rain, and he can calculate all the linear projecting once. But before we usually use HEC-RAS, as you know, HEC-RAS you pick location by location. So it is a new method, this rain on grid. It can be helpful, but we use it very often just to visualize where water is going. For example, if we need a big culverts, if the water is concentrated in one place or spread, as we are working in deserts area for most of the time. And for the dam resolution, we used only this purchased one of 5-meter resolution. I don't think it is giving accurate results. Sometimes it varies. HEC-RAS, for example, is giving 600 cubic meter, and rain on grade is just 1 or 2 cubic meters. So it's a big difference between the two.
Wow.
And we don't have anything in downstream, for example, to calibrate and try to arrive to the measured value. So we have just to trust our parameters and go with the value that we think it is reasonable.
Yeah, that I've heard that a lot on rain on grid, and Manning's Inn is a big deal too with rain on grid, because there are those really shallow flows that sometimes people find it difficult to get their Manning's Inn calibrated correctly. But thank you so much for sharing that experience with yours.
Yes, thank you for your answer. Thanks.
So 2D modeling is great, but there are, of course, limitations. One being that it can only compute one water surface elevation per time step for each cell. And that's no matter what program you're using. It computes one velocity for each cell face per time step. And I think the most major limitation is that you cannot change Manning's Inn with flow depth, because Manning's Inn does vary with flow depth. You just have to try to calibrate your model the best you can. And also, your SA2D area connections must be higher than adjacent cells, but that's usually pretty easy to fix. Let's see. Okay, so I will get into some 2D theory for the next couple of minutes. It's just good to understand what's going on. I don't know very many hydraulic modelers that like use differential equations on a regular basis. It's just good to know how the parameters affect your results and just kind of what's going on in general. So everything in HEC-RAS is based on these shallow water equations of conservation of momentum and conservation of mass. There are a couple of different options for basically approximating the results, and one of those is the diffusion wave equation, which is the default. And that's because the Army Corps recommends starting off using diffusion wave as you're stabilizing the model, getting initial results, fixing errors, and that kind of thing, and then switching to full momentum, which will give you the more accurate results. Always run your model using full momentum before submitting, because that's kind of an easy comment that people or review agencies will make. So here's kind of the more hairy conservation of momentum equation. And here's the terms, right, that we consider. It's based on Newton's second law of motion, and it's nonlinear and a function of both velocity and water surface elevation. And then, of course, the conservation of mass or continuity equation. And the diffusion wave approximation takes out these local acceleration and vective acceleration terms, and then also viscosity and Coriolis. So although it is faster and more stable, you're not going to get the effect of local acceleration and vective acceleration. And you can see this visually in the results. If you turn on particle tracing, you won't see the eddies or the little swirls, for example, near bridge embankments. And this is ultimately what it comes down to. Water surface slope equals friction slope. And this is how a mesh is set up in HEC-RAS. It's a series of cells, and you can only have 8 sides per cell. The model will not run if you have more than 8 sides. And when you're drawing your mesh, that's just something to consider, because if you put in a bunch of vertices, you'll have a bunch of little small faces at your boundary condition, and that can cause stability issues and just weird things in general to happen at your boundaries. So, yep, cell center and cell face. There's a water surface elevation computed for each cell center, and then velocity is computed over the cell faces. So you can kind of think of it as a cell face is like a cross section in 1D. So you want your cells and your cell faces to be aligned in the direction of flow, kind of like if you were drawing cross sections in 1D. And another thing to remember is that HEC-RAS uses this subgrid technology, which makes it a little special compared to some other 2D packages. While some other packages, they'll just assume one elevation per cell. HEC-RAS builds these curves for each cell. And it's a detailed elevation versus volume and some other hydraulic parameters before even running the program. And this is beneficial because it allows you to use larger cell sizes without losing any detail of that underlying terrain. That also results in smoother inundation boundaries because it's not just like rigid around the cells. It's not blocky. It's all within the terrain, and of course, faster run times. I don't know if I mentioned this before, but 2D models run much, much, much slower than 1D. You run a 1D steady model, that probably happens in seconds. Not so with most 2D models. It's a lot better than it used to be, but some models take hours and really big ones can take days to run. So minimizing run times is definitely a part of 2D modeling and something that we worry about as 2D modelers. So with all that blabbing about what goes on underneath the black box of HEC-RAS, this is kind of the 3 things that I'd like you to remember. In HEC-RAS, a cell is like a bathtub. You have a cell center in the middle of the bathtub. That's like your water surface. And water can go in and out versus cell via the cell faces. That's kind of like the boundary of the bathtub. So 1 average velocity per cell face, 1 water surface per cell. And then, of course, the results are more accurate if you align your cells with flow direction, which you can do using things like break lines, and I'll talk about that later. So here are the high-level steps for building a HEC-RAS 2D model. First up is putting a projection file in RAS Mapper, adding your terrain, generating a mesh, adding all the other things, creating your flow, data, and boundary conditions, and then running the model and refining as needed. And then this last step kind of sounds similar to step 8, but QA/QC would mean somebody else taking a look at your model. These models can take a long time to generate, and people get really hyper-focused and get their head in it, that it can be really hard to see things that are obvious to people who have I guess, a fresh set of eyes. So I always recommend getting a fresh set of eyes on your model before submitting it to a client or a review agency. So I'll kind of blast through this so we can get in the software. But the first step is adding this projection file in RAS Mapper. And that makes the model geospatial. And you have to do that before you add terrain or anything, because then the model will not work. The thing I would say on adding your projection file is that a projection file's extension is .prj. But what else is .prj? The HEC-RAS project file, right? So it can be confusing. The way I get around that is I create another folder within my HEC-RAS folder that says projection file, and then I put it in there. And that way, if I'm sharing the model, there's no confusion and it's very easy. And then I guess I should share, where do you get a projection file? I just typically take one from a shape file that's in the same projection as what I want my model to be in, and then use that. If you don't have that, there's a website called spatialreference.org, and you can download projection files there. Okay, yeah, and then one more thing I just remembered. If you are using CAD, I guess this will go more into the terrain section. If you are using CAD surfaces in HEC-RAS, sometimes the projections associated with your terrain in AutoCAD are a little bit different than what you'd use in like GIS or this. It has to match pretty closely. So I usually just reproject AutoCAD files in GIS before bringing them into RAS Mapper, and that prevents a lot of problems. So to add your terrain, you just go project, create RAS terrain, and then you pull it in. A couple of things to note: your terrain has to be a raster. It cannot be a TIN file or anything like that. It has to be a raster, usually a .tif or a TIFF file. And what else? You can also change this rounding precision to 1/128. I think there's one more you can go higher than that, but 1/128 is good, and a lot of people use that. And then another thing I found on this vertical conversion, if you have something in UTM and you've converted the vertical portion to feet, I would make sure this says no conversion, because HEC-RAS has automatically converted those files on me before, and then you get some really weird elevation values. So, and then next you would create your mesh. You can do it in RAS Mapper or in the geometry data editor. If you're a GIS user, I would probably just use the capabilities in RAS Mapper. It's very similar to GIS. You just right click, edit, and then draw. And as you're drawing the perimeter of your mesh, just keep those rules in mind about cells only having 8 faces. If you create sharp edges, that can create problems on following this rule. But at the same time, if you just click, 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 and create a bunch of vertices, that can make it overly complicated and create some stability issues. One way to minimize that is in this 2D flow area editor. Click the settings and then change this min face length ratio to something between like 0.15 and 0.25. The default value is 0.05, meaning the smallest face of the cell can be 5% of this size. That's pretty small. And if you have a bunch of little small faces everywhere, that can create some errors, and it can also take the program a lot longer to run because it's calculating velocity over a bunch of little areas. So change this, and just play around with it. But I found that 0.15 to 0.2 is a good way to go. And then of course, creating a good mesh is an iterative process. Start out with a higher number, run your model, see where you need more detail, what looks weird, and then refine from there. And then if you're going to only use one Manning's N value, you can change it here. The default is 0.06, which is pretty high. Usually you need to go lower than that, but we'll talk about that in another slide. So a common question I get is, what's a good cell size? And like a lot of things, it depends mostly on your terrain features and the size and shape that you need to accurately depict the flow direction. So if you have an area where water surface changes, the water surface is going to change really fast, you need a smaller cell size. And just remember, there's a single water surface computed for each center. So if your cell center is really far apart, that means you're not capturing maybe the differences that happen between that. So just keep that in mind. And then if you have an area where you need smaller cell sizes, just take a look at that transition, because that's where a lot of errors and instability tend to happen, is when you're transitioning from small to large cells. And then next you would add your 2D bridges using this SA 2D area connection. And then you would make sure that you enforce that along your mesh, otherwise flow over the bridge won't be captured very well. What else? One thing I'd like to mention is that a lot of times people forget to use multiple opening analysis if they have a bridge opening and a culvert, but HEC-RAS will not automatically capture both of those. You have to use this multiple opening analysis and say, okay, this is a bridge, this section is for a bridge, this section is for a culvert, and specify that, or it'll only go through one part and you'll miss the effect of this relief culvert. Yeah, and then just a reminder that if you want to capture what's going on around the bridge embankment, and you want those eddies that happen around a bridge, you have to use the flow momentum equations, or you won't get that information. And then you would adjust your Manning's N value. Like I said before, 0.06 is the default, but that's really high. And they do that because higher Manning's N values do correspond to more stability usually. So you could start off higher and then lower as you need to. One thing to note is that 1D Manning's N is different than 2D. That's because although we call Manning's N like a roughness coefficient, it's really just a catch-all for all uncertainty, right? But the 2D equations, they account for a lot more, like that advective acceleration and local acceleration, that the 1D equations don't. So therefore, the catch-all value is just different. And in general, Manning's N values for 2D models are about 15 to 30% lower than 1D, but the HEC-RAS 2D manual has a good guidance section for Manning's N values, so just check that out. And again, remember, your higher depths will have lower Manning's N values, so if you have a channel that's pretty deep for most of the simulation, consider lowering the Manning's N. And then as far as adding your flow data and boundary conditions, this is where you would do your rain on grid if you were doing that using this precipitation right here. But most models, you'll have a flow hydrograph on the upstream and then a normal depth or something like that for the downstream boundary condition. This normal depth boundary condition, it can be a little difficult to get it right. So I would suggest bringing your downstream boundary condition far away from your area of interest, at least far enough where it's not affecting your results in that area. Let's see, okay. 1040. So next you would do your run file. And this is what it looks like. Your starting and ending time, which need to match your flow hydrograph in the other editor I just showed you. You choose your computation interval, and then you can do options, computation options, and tolerances, and then there's all these different things you can do here. The most important is, again, this equation set. The default is diffusion wave. but you'll want to change it to SWE-ELM during your final run. There are some cases where you would use the other two, but this is definitely the most common. For the vast majority of applications, it's going to be SWE-ELM. Let's see, there's also these that help with warm up if you do that. Your tolerances, and then there's also an option to use this advanced time step control, which I didn't put a screenshot for, but it'll use the current number to change your time step throughout the simulation, and that can really reduce your run times because the program will shorten the time step when necessary, and then it'll make it bigger when that's appropriate. And then there's a lot to do with refining a model, but the most important, I would dare to say, and most common thing you would do is use break lines to make sure your flow is aligned with the direction. Yeah, make sure your cells are aligned with the direction of flow. So you want to put these break lines along streams, levees, roads, berms, that kind of thing. And then in RAS Mapper, you can turn on contours that are very high resolution, and that helps you make sure that you're getting your break line in just the right direction or just the right spot. This is just a recap of the workflow I just went over. It is definitely an iterative process. I don't know if I've ever created a 2D model in one swoop and then just had it work perfectly. It usually takes a lot of iterations to get everything just right and the way you want. And yeah, I think that's all I got to say about that. I know I just blasted through a ton of information. We only had an hour and this was very high level. If you are interested in learning more about HEC-RAS 2D, I'd recommend checking out this one-day course I'm offering in July. Because you've attended this webinar, you can get a 20% discount today. Just scan the QR code, and I'll send out this presentation after the webinar, so you can scan it then if you want. And of course, if you have questions about what I've covered today or about the course, feel free to reach out. I love talking to people about this stuff. And I guess with that, I'll open it for questions or just start showing you around the software, whatever you guys would like to do. All right, well, I don't see any questions right now, but definitely feel free to do that. I guess I'll just open up HEC-RAS and kind of show you some stuff that I just covered during the presentation, and I'll keep an eye on the chat. Oh, that's not. Okay, so here's an example of a project I've been working on recently. As you can see, here's the mesh, here's my break lines, downstream boundary conditions, upstream boundary conditions. And if you zoom in, you can see I've used two different terrain data sets merged together. You can kind of see where the survey data interfaces with this more coarse USGS DEM data. And if you're looking at terrain in HEC-RAS, one thing I find really helpful when you right click is to update this legend with view, because the colors update and this legend updates as you zoom in. You can also just, with your cursor, do this and it'll tell you what the elevation is. Another thing that's really helpful, like I said earlier, is adjusting these contours. So if you're drawing break lines and you want to get them in just the right spot, you can turn on really high resolution and make sure you're following, for example, maybe I'll fix this and then it would really follow these contours perfectly and make sure flow is aligned. The cell faces are aligned with flow. What else? So another cool thing is that when you put this projection file in right here, you can then use these map layers, and there's a ton of base files that you can download in RAS as backgrounds. Your typical ArcGIS data. You can bring in Google Maps, Topo, all very helpful. And Army Corps of Engineers is looking at even improving this further with RAS 2025. So that should be exciting. Another thing I didn't really cover in my presentation is viewing results. So when you run a model, you get water surface elevation, maximum velocity, and maximum depth that show up right here. And there's things you can do there. You can use this animation and it'll show flow coming down your model. That can be pretty helpful. Okay, good question. Where do you use a 1D and 2D combined model? That can be really helpful. For example, if you have a very 1D stream that's really long, but then it drains to an area that's maybe more of a dispersed flow area, you can connect your 1D to a 2D area and then connect it again to 1D. It can get a little tricky though, because of that interface between 1D and 2D. And you do have to have everything in an unsteady flow model. So what you would do is you would take your cross sections right up to the end of 1D, and then your downstream cross section would line up perfectly with your 2D so that it would drain in, and then same thing on the downstream side. Why not use a full D then? Do you mean a full 2D? Yeah. Why not use a full 2D? I mean, honestly, that's probably ideal. If you don't have terrain data for the cross sections upstream, or if it's a really big stretch of stream where the runtimes would be obnoxiously long, that would be a situation where you might want to use 1D, 2D. But yes, the combining 1D and 2D is annoying because of that. It's that interface between 1D and 2D where RAS is trying to change equations. It's finicky and it can take a while to get right. Are bridges still 1D, 2D connections in the most recent version? Yes. Yes, I can show you that. Yeah, so even in 2D, like, okay, let's say I wanted to add like a bridge right here or something. You would do something like that. Man, I can't. Yeah, and it would come up with this. The thing that is different though that you have to consider is the weir. Man, I'm not clicking on the right thing. Is the weir equations when you're modeling it. If your model is going to pass through critical flow, just make sure you click use weir equation instead of use normal 2D flow equations. Oh wait, Hello, I'm still an undergrad. Oh. Can you make a small suggestion that would help me to make my paper more accurate? Could you give a little bit more detail on that? Yes, you can use HEC-RAS in pump storage projects. There are capabilities with pumps. See, pump station. Are blocked obstructions and ineffective flow areas different in 2D? Yes, you don't define ineffective flows in 2D. The equations do that. If you have obstructions, it's best to use like these 2D or these terrain modifications, and you can actually put in the obstructions. For example, you could put in some woody debris, a rectangle, raise the elevations of certain areas. And then the program will measure the flow around that. Let's see. Any other questions? I'm gonna pull up a project where I have a 2D bridge. How can you know when your model is unstable or stable enough? That's a really good question. Well, first of all, if it is unstable, you will get errors and the model may not even run. So if you're getting a lot of errors that the water surface difference is way too high, or that HEC-RAS went through a bunch of iterations and it can't solve the equations, that's one way. Another common problem is there's pulsing. So if your Courant number is too high, see, come back to this. If your Courant number is too high, and then you run your simulation and you have, say, like a profile line, this would pulse. The flow would go. So one way to check that, that's really easy, is to go to your thing. You can do create new results map layer, and then there's all these options, right? But you can do face maximum Courant, and it'll actually show you where the Courant might be higher than you want. If you really want your Courant number to be around 1, it can be lower, but you don't really get bonus points in accuracy for that because the program's calculating one water surface per time step, and it's working well. So that's an option. You can also, what else? Do this maximum water surface error, and it'll tell you where the program's going wrong. Usually it's around these internal boundary conditions and the external boundary conditions. I'm working on a flood risk assessment on a school located near the sea. Okay, near the sea. So a small suggestion I could make is to do a sensitivity analysis and determine how changing things like Manning's N affects the results, and make sure those parameters are very defensible. Are there any other questions? I think I was showing that 1D, 2D bridge. Yeah, so this is an example of what a bridge would look like in HEC-RAS. It's very similar to 1D. It's these overflow computations that are different in 2D. In 2D, you can select normal 2D equation domain, but I would recommend only doing that if you know for sure that the bridge will be pretty much submerged most of the simulation. Otherwise, it's good to just use the regular old Weir equation. If there's a waterfall, like if the water's gonna, or if, yeah, it's going to pass through critical depth. Anyone else? Any other questions? Anything you wanted to see in the model? Why not use 2D equations in overflow? I'm not saying never use the 2D equations in overflow. It's just the 2D equations don't work very well when there's a waterfall. So because it doesn't work very well with super rapidly changing water surfaces. So if you have a weir and then the water is just going to go like and plunge down, the 2D equations just aren't very good for that. But on the other hand, the Weir equation isn't very good if this culvert was like submerged the whole simulation. So you just have to understand your model. Could we see a final product of something you could present to a town from HEC-RAS? I don't really have like a present, but this is something I presented to a client yesterday in a more informal setting, I guess. And one thing I like to show them just starting off is to turn on the imagery and then just do this little animation and maybe even turn off this because it's a little distracting. And then it just shows the little animation of how things flow and what's going on. And another thing that's useful to zoom in and even take a screenshot of is to turn on this particle tracing. See, because then it just shows like where flow is going. And clients really like that. You can also export this to GIS and create exhibits that way. I prefer that more than, I don't know, presenting screenshots, which I know some people do that. How do we take into account groundwater flow? Yeah, you can. They have infiltration. There's infiltration capabilities, Michael, but there's not really a way to model groundwater and surface water together. But there are infiltration capabilities in HEC-RAS. Yeah. Yeah, HEC-RAS is pretty awesome, and it's come a long way, Tommy, for sure. Let's see, well, we're almost at time. Does anyone else have a final question before we close? Anyone? Well, thank you again, everyone, for coming. I will send you a link to the slides. Have a great weekend. And again, feel free to reach out if you have any questions about what I covered or the course or anything like that. Thank you and bye, everyone.